So welcome back everybody. So let me do a quick recap on what we did last day. So Thursday we saw a little bit of the theory of thermal simulations and we saw some physics principles. Then yesterday we presented you the Ktirio software and the project and what we are doing in the project of HiDALGO2. Then we did some exercise on building optimizations. So we will present you uh, the parts about the ensemble simulations that we ran with Ktirio Urban Building. So it will present you how we managed to compute uh, several simulations in parallel with scenarios about uh, vary the parameters of the buildings, such as the insulations, the thickness of the walls, the conditions of the instructions for heating or the ventilation. So Gwendolyn will explain that in the first presentations. We will then be running Ktirio simulations on Carolina, such as the same as did yesterday. So we will try to do it together. Uh, and then we will analyze a notebook of uh, simulations with some analysis of the variability of the parameters for the simulations we will run. So we will run again a simulation on Strasbourg. It will be 1 kilometer diameter, so there will be approximately 1,000 buildings, certainly a little bit more. So we will analyze some graphics about the result of a single run. So it will not be an ensemble run. It will be a single run, but we will observe some variability between the buildings and what happens in the district of Strasbourg. So if you're ready, Gwenolet, maybe you can start. So let's go for it.
Okay, so we have seen how to simulate a building, and we have seen that we need to know a lot of parameters to accurately simulate a building. But in our case, we want to simulate a city, and we can't go from building to building to get all the necessary parameters for the simulation. And so rather than doing a single deterministic run, we are currently working on running some ensemble simulation. So rather than simulating the city once, we simulate the city a number of times, each time varying some parameters in order to obtain a statistical point of view of the city and to have some results that are closer to reality since we can estimate the margin of error for our results. And without having to go to the streets and try to figure out which building has which material. So to run an Ansible simulation, we first have to know what kind of parameter we will be varying and what will be the distribution for each one of those parameters. What is quite interesting is that in a city, we will use both the most common type of distribution. So the normal distribution um, and the discrete distribution. So to ensure the ensemble is relevant, we must fit some realistic data, and so we will distinguish between those two types of parameters. So for parameter like ventilation or airflow rate, we often use Gaussian law because physically a mechanical system will subtly vary around its set point due to system wear that will create some difference in pressure and depending on the filter status, if it's more or less dirty, the set point, we will have a variation around the set point that will be close to a normal distribution when we look at the city as a whole. But when we want to model the wall of the different building in the city, we can rely on uh, categorical variables, so discrete distribution, because for building envelopes such as insulation thickness, the variation is discrete since industrial materials are produced in mass and they come in standardized sizes. So we do not want to simulate a thickness that doesn't exist on the market. So after deciding the type of parameter we want to vary and the distribution law, we have to decide for the whole city how we distribute those parameters. So we either got a global scope or we've got a per building scope. So the idea is for global scope is to identify some parameters that we want to, for which we want to measure the impact. So real life application could be the grid carbon intensity. So since the electricity is naturally produced, it's the same for every building in the city, the carbon content. But depending on the type of electric production that is running, we can have varying carbon intensity for the electrical power. And so we can run several runs for the same city, but varying the, the carbon intensity for electrical power. And for the per building scope, we have some variable, but this time we distribute it in independent manner for each building in order to simulate different scenarios for different buildings for the whole city, and then we simulate a number of runs varying those variables independently for each building. So the use case could be, for example, occupant behavior, which is very different from building to building. And it's able to capture for the real world, the heterogeneity of the city and occupant behavior. So in order to run this simulation, we use HPC machine. To simplify the architecture, what we have is we divide the node in different worker groups. So for a same city with different parameters, so city A, B, or C, which is the same, but as we said, different parameters, we simulate and we have some data that are collected. And rather than storing directly the data on the HPC storage disk, we use some algorithm that help us to compress the data because if each one of the worker group is trying to directly store data on the disk, the load will be too high and it will probably crash. So using dedicated nodes for input-output, we can run some algorithms such as the Walford algorithm, which will aggregate the time series in a one-line algorithm, and it will calculate the mean and the variance on the fly, step by step, for the simulation, and the memory complexity will remain constant for the storage. And finally, as I said, we aggregate the data, and it's necessary for performance because if we use raw data, uh, it will it will be too much to handle for the HPC disk. And so we have a different mode of aggregation. So we want to aggregate the data at the building scale. So we are only doing temporal compression to obtain some relevant KPI for the building. So for this, the use case is to find the hotspot in the city and to see which building will need retrofitting inside the city. And of course, as we are running Ansible simulation, we can have for each building a certainty. We can quantify the uncertainty and say to which degree we are sure that this building will need retrofitting. Um, So the second mode of aggregation will be so temporal compression and spatial compression. So either at the district scale or the city scale. So we do this for two different use cases. So if we aggregate at the district scale, it would be quite useful to discretize the city in districts and to quickly identify which districts are potential heat island, especially heat island coming from anthropogenic causes. So the energy necessary for cooling the building, we can calculate that, and so it will give us a heat map for different districts with buildings that have the most energy consumption during the summer. And finally, we can have a global view at the city scale, and it can be useful for this for policy and decision maker to have some different KPI and to track progress for the cities and to reach the set target to form. So yeah, you navigate the 2050 climate targets. So I didn't want to be too technical for this presentation. I think that most of you know HPC machines, so you should be familiar with ensemble runs, but I wanted to do a quick recap. Currently, we are working on this. We are close to run some simulation on our use case. Uh, but unfortunately, it's not stable as of yet, so we won't be able to give you some code to run. But we're very close. So maybe next year we will be doing another session, and this time we should have a stable ensemble simulation. So if you remember my introduction in the first day, I started my introduction by giving a warning. When we simulate models, we are directly tied to a broader context. And so when we do simulation, we should reflect on the potential use of our model. And so I wanted to bridge my first introduction to the end of our seminar by introducing the relevance of city-scale simulation, and so the relevance of our work and how they integrate into the real world by describing the benefits of our work for different use cases. So as for now, the software is still in development. So the subject I will talk about are mostly perspective for the future. But I hope it can give you also some ideas for model development. So we introduced yesterday with the fact that we are working on coupling with other pilots inside the HiDALGO2 project. Those coupling are bridging a gap between two traditional silos in building simulation in order to optimize energy efficiency and urban resilience. So the traditional silos that I talk about uh, are the energy studies that are conducted nowadays are conducted in isolation. So you either have some studies that are done in the building sector, which is mostly private, and those, and as you can see on these images, when we simulate a building for someone, we don't represent the direct urban environment around it. And so we ignore the impact of a building on the public urban scale. And on the other hand, when we are running urban analysis, we also ignore the effect on the building consumption. So it's not quite clear when we look at these images, but what you should know is that each of these buildings is not simulated. It just has a constant value for its temperature, and they don't represent the fine detail of the building simulation. So the figure of the sun, so this software that you are seeing right here is a software that is called Pléiade. So it's the software that is used in France because it's a software that was developed for France regulation. So this diagram of the sun that you can see represent the different path of the sun for the different months. So at the top, it's the course of the sun during the, I can't find the word, but during the summer, the sun will be at its highest on this part of the curve. And when we get close to the winter, it will follow this curve and get back to a lower angle and then go up again during the comment est-ce qu'on dit printemps? Spring. Sorry, thank you. So it will go up during the spring. And so you can see here is the east, and so it rises in the east and it sets in the west. And so it's calculating using the sun trajectory. And its formal name for this type of graph is heliodan. Can I type this? So, as I said, we are trying to bridge, okay, no, I didn't finish for this, but we are trying to bridge the gap between the private sector and the public sector in order to calculate the effects of renovation on a building on the urban scale and renovation on at the urban scale on buildings. And so by doing couple simulation, we can quantify the impact, the reciprocal impact on the microclimate from the building and on the building from the urban renovation. So the idea behind this is if we are talking to a policymaker, we can also help policymakers to have a more comprehensive approach on the valuation of public investments. So one problem that is becoming increasingly worrying is the energy precarity. So what I'm showing here is some graphs that illustrate the number of intervention for unpaid invoice. So you can see that more and more people have their electric supplies cut off because they couldn't pay the bills. So this is for the winter time, but we don't have data for the summer months. because during this time, so what we can see is that people that have to pay higher prices for bills have poorly insulated buildings. So if we cut the electricity during the winter time, you can expect that during the summertime they will have the same problems, but they won't be able to maintain their buildings at correct temperature. So it's becoming a very worrying problem because so this is the data for France, and you can see that the gas consumption, we don't have an elevation of the number of intervention, but for the electrical consumption, there is an increase. The reason is we can talk about an increase in energy poverty is because in France we do have a lot of houses that are heated via electric radiators. And so what we show here with this graph is the direct impact of cutting the electricity supplies on households will create precarity for a lot of people. And so if we are able to simulate the impact of public renovation on the buildings, we can give we can help decision maker to evaluate the public investments by doing some urban renovation on some vulnerable on some district with vulnerable household, and we can provide metrics to calculate the number of degrees that will be reduced during the summertime when you renovate the urban space. And thus we can bridge the calculation of energy performance to metric of private, social, and economic metric. So we help decision maker to make some decision based on more accurate data, and we help and we are trying to help them alleviate the actual crisis on energy consumption. So that was the first use case, and that's why it's kind of interesting to try and do couple simulation between building and city. The second use case is the district heating investment. So district heating is something that is more and more common around Europe. So the idea is that you decentralize the heat production. So you produce heat using power plants, and you circulate this heat inside pipes around the city, and buildings connect to those pipes with a heat exchanger, and so they don't need boiler anymore. And the challenge for investing in new district heating network is the infrastructure. So this type of endeavor is very capital intensive. And the current demand forecasting is based on limited historical consumption. So what they do is they do a door-to-door survey, and so they can aggregate data with the data that they have collected for a district. And based on this data, they can calculate if they want or not to deploy a new branch for the district network. So with our simulation, we can run an ensemble simulation, run different scenarios for the buildings in the districts they want to connect to. And rather than having incomplete data, because when you do door-to-door survey, you don't collect a lot of data, what we are able to do is to give an output with statistical and uncertainty quantification that is given with this output. And so they can run a benefits risk analysis of deploying a new branch for the district heating network. So that is the use case for the investment for district heating. but we can also we can also provide digital twins. Um, so the idea behind this is that district networks needs to rely on fossil fuel to heat up during the peak load. So you can see on this graph that they try to use as much renewable energy sources as possible, and then they deploy some non-renewable energy sources in order to palliate for during the heat peak. During when the temperature drop drastically and the energy consumption gets quite high for the buildings, they need to start powering plants using coal or gas. And so having a digital twin for those networks, we can run some simulation on 24 to 48 hours in advance. And so they can pre-charge thermal storage or ramp up cheaper, cleaner energy sources based on our simulation. And they can shave the use of non-renewable energy sources to manage those peak heating loads. It's also quite a good tool to use because nowadays people tend to install a lot of new renewable energy sources on the roof, so mostly thermal panel, and we want to be able to simulate the installation of those new systems on and the impact on the district network. So having simulation then can be run either on ensemble runs or on deterministic runs, and using prediction model for climatic data, we can provide a comprehensive tool for the district heating networks. And actually, it's a tool that is lacking for them because it's very labor intensive. They have to do some modelica models that are produced by hand. And so we can produce those models directly using the Ktirio framework and quite quickly. And finally, the last case that we are working on is doing a mass screening of buildings. So using ensemble simulation, we can provide some regulatory APC. So, for Europe wants to do this kind of lettering for buildings, and they want to harmonize the lettering for every country in Europe. And so, what we want to produce is a non-binding version of this APC, but it will be a useful strategic planning tools because it's a common KPI for a decision maker, and it's a very easy to understand KPI for the common public. The key innovation is the statistic run that we are doing. Since urban data, as I said, often contain uncertainties, and even when we are doing insight calculation for those kind of statistics, there are a lot of uncertainties because the people that do this have to do this quite quickly. Running ensemble runs will allow us to produce a confidence interval and different probabilities for the lettering of each buildings around the city. And so we can screen massively, consistently also, because we can run our ensemble runs using the regulatory calculation. Even though it's not legally binding, we can still use this calculation to calculate the letters. And in the end, we can provide heat maps and we can provide a level of uncertainty for each building, and the decision maker will be able to target investments more effectively. So that's it for my part. I wanted to do a brief explanation of those different use cases. So maybe to inspire you and to explain the potential use of HPC machine in building simulation and to provide some use cases for the ensemble runs. So I will let maybe Philippe speak to introduce what we'll be doing for the next part.
So we will, excuse me. So we will launch deterministic signal simulations on Carolina, such as the same I did yesterday. So if you have your logs to connect on Carolina, please, you can start to connect with your IDE. Yeah. So does everyone have their password? And does everyone have their reservation for a computer node? I will share my screen now. So we will simulate and we will start when the simulation will be done, we will download the exports and visualize on PowerView. So you will manipulate a little bit, and after we will give you a notebook to continue the analyze of the simulation. We will not give you the notebook, sorry, but we will present you the notebook with another analysis. Okay, so let me share my screen. Okay, so I will need to interact a little bit more with you. So please in the chat, tell me just write okay if you can connect on Carolina. So are you using Visual Studio Code or another IDE? Okay, thank you, Bart. Uh, does the others is connected? Okay, Marco, thanks. Okay, thanks, Andre. So so in my terminal, I am at the root of Carolina, so I think we can go on Scratch. So maybe when you launch Carolina, you are in your home. On my side, I was in training. Training and I was with my user account, so I think I was, no, it was not this number, but it's not important. So you can go on Scratch. Yeah, because this is my own. You're right. So I'm 185. Okay. Thank you, Bart. So let's go on Scratch. So from the root, Scratch, we can go on project. I will put the path in the chat. So we can go on project and ATR 25.5. So once we're there, uh, so I have created a folder with the data inputs you will need to simulate uh, Strasbourg simulation in Strasbourg. So there are many files like the meshes, some scenarios, some FMUs models, some weather data. So you don't have to change anything in the data sets. So I think up this. So you can create your own folder and we will manipulate there. So maybe you can put your your name or family name. I wrote my first name. So let me just write in the chat the path. Path on here, you create your own folder. What was the SSH command to Carolina? Can you pass into the chat? So the SSH command to connect on Carolina? Yeah, thank you, Bart. So let me check up. So yeah, no, normally uh, if you have created your public and private key to connect on Carolina, you should have. I created a private key and a public key to go on Carolina. I call that ID RSA 94I. And then we can print the config, I think. Uh, so I put host like this, and I put the host name to connect on Carolina, then my username, and I put an identify file with my private key. And then normally after that, you can just run this, or you can do with your username arrobas carolina.84i.cz. Is it fine for you, Volkan? Let us know if you if your username. You should have received a mail with your username. I think maybe Lucy
Yes,
can
you receive it in an informational email, but I can check it for you. Just give me some minute.
and everyone has a reservation to to a special node. That's right. So now I see there are some new folders, so it's perfect. So now we should, I will create another molecule. So let's go like this. And now we should download the obtainer image. So let me check the command Mm. So normally you should enter module load container. Let me check it right. Yeah. So I will share it in the chat. Give me 2 seconds. Oh, right. And then normally we should pull the obtainer image. Okay, so from my side, I think. Oh, sorry, I forgot. I forgot. How is the command to delete? I forgot to enter in my folder. It should be removed, I think. Okay. So normally go in your, sorry for that. Go in your own folder, and then I think you can put the obtainer image. Let me write it in the chat. So let me know if it's good for you. Uh, I'm not sure we can use the same one. I'm not an expert using the obtainer image, and I'm not an expert of obtainer, but the download should take 3-4 minutes maybe. It should be quick, I think. And it makes us do the commands, so we can repeat these commands on other computers if you want. If you want. So then I will prepare you script. So you get an error, right? Failed to authorize. Okay. Okay, so does everyone has the error? Uh, Sorry, so we can use we can use the same image. So sorry for that. Let's just I will put the image on the same folder. Okay, so now okay. So now let's start to prepare the shell script using Slurm. So normally we should everyone should have a reservation. So let's create another Slurm. So or we can call it Ktirio. Let's call it Ktirio. Ktirio. So you can create your own shell script in your own folder. So we will share the same Aptainer image. So sorry for the 5 minutes delay. I wasn't sure. So we will keep your own folder in the training ATR 255 folder, and then you can create a shell script, and I will put a base script to download on the chat. So let's do it together. So let me first everything. So reservations. So account, I put 8 year 25. What are your name accounts from your side? Does it start also with ATR 25? Yes, okay. But then the number is if okay, yeah. Okay. What is the path to this script? So which script you mean, Bart? The script that I'm writing right now? Yeah, I will put it on the chat, and you can or you can go in my once we are finished. So will I will do the basics for you, and there you will copy paste and finish to editing the script. So I think you can call with a job name. You can put your username if you want, or your first name. Number of task 64. It's fine. It will take like maybe 3 minutes. CPU per task. So there it's where the basic output, so the standard I don't have a word in English, so but you will have a different display there in this file in your own folder if the simulation is doing well. We can put a timeout of 10 minutes, it's fine. Normally it should take less than 10 minutes. If you want, we can put 20 minutes to be sure. Then you will put your reservation. Put your reservation. Yeah. Okay. Put your reservation. Okay, so load obtainer, load opening API. So we run S run obtainer exec. So we should all define a new home for our outputs. So from my side, I can create my new folder. It's my second name, my family name, and then we will create an output directory where your results of the simulation will be there. So next, so you don't have to change anything there because this is the absolute path for the inputs. So you don't have to change this one. And then scratch projects. You can put the path for the obtainer image. So normally it should be that now. Now the program we execute is called the field PPQ city energy model. So we will put config files. So we will put, so you don't have to change that because now this absolute path will be, we will use this one to call this one. We have bind it. So input data, and so you have to put the path for the config files of the simulation. So it's called Strasbourg config files. And there is another config files because this is a version of Ktirio from 4 or 5 months ago. But we changed something now with our updates. It should be easier, but now for the moment you have to choose to put a second config file where you can find the physical models, the FMUs. So we saw years ago. So in this config files, there are some FMUs that will be used for the simulations. So basically, there are 10 FMUs with an ideal heating. Yeah, I will copy the script in the chat, of course. And what should be the name of the script? So as you want, you can call it like uh, how you feel to call it. It's not so important. From my side, I call it Ktirio. The important thing is to put it in your own folder. So we'll see that. I will put the script and I will do the same as you in another folder. So input data, so ideal heaters. So we will start with ideal heaters. Maybe after we can test with boiler heaters. It will take much time because it is real heaters and not ideal. So there are more and more equations, but we can test after. And so we have to define the same database directory. So it's the same for the output data. So your username, your uh, your folder name, so folder name, and you can do this also. The folder name and the directory should be the same. So let me erase this and put your folder name. All right, so now we should be fine. So let me download it and share it. Yeah. Hey. So, tu, 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 tu. Carolina. Input. Okay, perfect. So, can you share it directly? I did this yesterday. Okay. So now the script is in the chat. So I will do the same as you guys. So okay, I'm there. So let me open. So I have a new window. Okay, hello. Where am I? Okay, so uh, maybe I can go. I can open. So I put my family name. So I go on my folder. Yes. So normally you should not have this again. Delete because it's upside down. So let me put the script there. So from my side, I can call it FitPPQ Vincent. So I can put my reservation. So I can check my mails to see the reservation. So I have this reservation for today. So please check your mails to see your own reservation. Account maybe it should work if I put mine instead of 25.5. So I can put oops, my own uh, folder name. Also, I can put it so there and there. All right. Now, so it should be correct. So I will test it, but first let's create the output data directory. Let me just display the chat again. I lost you. Uh, those config files take absolute or relative paths. So it is an absolute path, but we bind it, this path, with now this one. So you just have to keep input data, so you don't have to change this one. Does that answer the question? Okay, nice. Nice. As control show reservation should also show the reservation. Oh, interesting. I didn't know that. So you mean in the chat I can put as control or I put it in the file? So I put my username. As control and you write show reservation. That's right? That's what you mean? Okay. Okay. Okay, thank you very much. I didn't know that. All right. So, as Bart said, as Bart has written it, you can write as control show reservations to see yours. All right. Okay. So now it should be fine if, let's try if I didn't forget anything. So let's launch um, the program. Okay, sorry. Let's try batch Ktirio on sh. Invalid account, so think I just have to put 25.5, right? Yes. There is no reservation name, but name. So Andrei, can you try this command of Bart? So S control. So Javier, unless the reservation is the same for everyone, okay? So they should have the same name there. That's right, Javier? Yeah, okay, thank you. So now let me check. So I can see not the full name, but it starts with UPP K, so it should be right. I can see it is running. Let me check so the outputs. So if you go in RFM job point out, you can see different outputs. So you can see that the program is loading and constructing from the data. So the constructor starts, then we create the partitioning, we collect the mesh, we collect the weather, the scenarios, then we launch when we init the building model, so the FMUs. So the FMUs, there are, for this simulation, there are 10 FMUs. It is in load 0, so the value of description 0. So it's very simple. It's bounding box. The difference between the FMUs is the number of thermal zones, of habitable zones. So uh, those FMUs, we can create a lot of instances from that. So from one FMU file, we can simulate a lot of different buildings. So yeah, so now this is the execution time. So you can see the computations time for some steps of the simulations. So we execute the solar mass computations. We 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 start by retrieving the solar position, and then we do the ray tracings. Then when the solar masks are done, we execute simulations of buildings. So we do one time step, and we provide the inputs, so the weather inputs, the solar mass inputs, the scenarios instructions. So this is done using FME4CPP for interacting with the FMU. So it's a library to interact with FMU in C++. Then we have a post-process part. So we start to write the reports, and we start to write the visualization file. And then you can see that for each time step. So you can update it on the left, or maybe if I close and I reopen it, it is updated. And now I see the simulation is done. So it is a simulation of 1 week in January. So if some of you have succeeded in running the simulation, and you can see the end of the simulations on your output file, please tell me in the chat. If someone struggled to launch the simulation, please ask me any questions. You're welcome. Let's wait 2 or 3 minutes, and then I will show you the output data folder. Yes, I think your simulation is still running. If you go on your folder and you open this file, and if RFN job out, point out, you should be able to follow the status of the simulation. And if you write SQ user again, if you see the time is updated, I think you should be fine. So yeah, the simulation take approximately 3 minutes on 64 cores. All right, so I see the responses of Bart, Daniel. So let's wait 1 minute more, and then we go into output data. Okay, so let's start with analyzing the output data, and we will export the PowerView files to watch the results on PowerView. So there you have save the different inputs of the simulation. So you can find the weather file. So we have the weather from 1 week. So you have the simulators, the FMU, and their descriptors. In our recent updates, the descriptions of the simulators are hiding in the FMU. So as I said, it's not a very recent update of Ktirio, but So there are some updates. Okay, so you can find the scenarios, the pre-processing, and if you go in instances, you can find a report. So this is a JSON file, and there are some outputs returning. So for this kind of reports, it's the mean of every building's value. So it's the mean of the temperatures in the city, the mean temperatures uh, on the exterior surfaces of each building in the cities, and so on. So from this kind of JSON file and reports, we can create some graphics. We have a library using Python and Antora. We can plot some graphics on our websites or just in Python notebooks. You have different HDF5 outputs. And then if you go on load zero export, so I can restart. So you go in output datas, instances, so NP64, and you have load zero exports, and you can find the different exports for ParaView visualization. So basically, I think you can download it, or if you know how to, I don't know if you can use ParaView on Carolina, but if you have ParaView on your own computer, uh, download the exports. It will take 1 minute maybe. So I will do that. The exports. So I download it. Once you are done, tell me. Uh, so for this short simulation, it should be fine, but when you are running very long simulation of big cities, we prefer to download the exports and the visualization results at each time step to be sure we don't lose anything, because it can be really hard to download a ton of datas like this. Download, okay, okay. Okay, so let me respond to the question. I am connected to text. Data or bulletin. Uh, maybe in your terminal you're not forced to download the output datas folder, but yeah, you can try to zip it or to achieve and to download this. But there you can go on instances.0 exports and you can download this one. So output data, we'll put it in the chat. Output data, instances, NP64, load zero, exports. So if your download is okay, let's start to open ParaView and open the exports. So I have opened ParaView if I'm too quick, I will reshow again. So don't hesitate to ask me if you want me to show again how I done that. So, uh, so let's open the export I have downloaded. So let me search it. No, okay. So you can open the cases, point cases file and apply it. So it's the same thing as I showed you yesterday. So if you have opened it in ParaView, tell me in the chat, please. You're welcome. And if you have some questions, please free to ask. Feel free to ask. So of course, this is very basic. So bounding box for a lot of buildings are a little bit far from reality, but it shows you the basics of the visualization simulations. We are currently improving our software and we can run now some simulations with level of description 1. We are currently working to include the roofs in our physical models. So next year it will be very interesting to see the visualization. We will have much more improved simulations. PowerView, okay for Bart. Okay. Daniel, uh, do you have downloaded? Oh, okay, fair, perfect. Andre, do you have succeeded in downloading the data? So there we go. So I like to, okay, okay. We will come back to you if you want in some minutes. I will start to show how to manipulate in PowerView. Uh, oh, it don't find your folder. Thanks, Spartan Daniel. Yeah. Okay, thank you very much. So if you are in PowerView, uh, we can manipulate. So you have the different datas for these simulations. So now we have solar shading coefficients. We have so ambient temperature is the temperature of the weather at 2 meters from the ground. So it will basically plot the same temperatures on every buildings. But if you go in exterior temperatures, you will see the temperature of the surface. So we will rescale the the data range because it takes into account the vegetations and the ground, but of course there is no outputs of temperature for vegetations. So let's start with the VTK composite index and we will create a filter because you will see if we, for example, if we want to display the solar shading coefficients, it will put the color on the terrain and we don't want that because we will not see very well the buildings. So I go on VTK composite index and I go in filters, alphabetical, and I choose extract block. So there in the properties of extract block filter, I will choose to show the building and the vegetation, but I can just start with the building. And if I apply, we can observe only the buildings. So let me just observe if it's okay. So you can observe that there are very, very small buildings. So maybe if I put temperature interior, so this field is for the interior temperature of the building. They are all in red, but some buildings are in blue. They have 0 degrees Kelvin, so there are no temperature data for these buildings. It's because there are filters. So as this kind of buildings are very small, we don't simulate them. And from OpenStreetMap, we can retrieve not only buildings, so sometimes it's other things that buildings. So sometimes it can be a bridge, it can be, I don't have examples, but it can be just really small boxes. So sometimes it's not buildings, so we we can filter them. So Gwendolyn is telling me that in Strasbourg this is elevators. So this is definitely not buildings. But if I rescale, for example, if I rescale for for example, so uh, like 17 degrees to point, uh, so 23 degrees, and then we scale, and we have much more different colors. So remember, it's ideal heating. So some buildings are heating the buildings at 18 or 19 degrees Celsius. Sometimes it's 20. So I will give the hand to Gwendolyn, where he will continue the explanations.
Uh, so as you can see, this is the city of Strasbourg. So you can see that the cathedral, which is the huge block, is modeled right now. But as we have said, we are able to filter the small buildings, and later on we will filter the buildings based on their types. So we don't want to model the cathedral. I'm mentioning here that we are modeling the cathedral because it will be relevant when I will present some KPIs later on after the break. So maybe you can... Tu peux appuyer sur play. So as Philippe mentioned, we are using some ideal heaters with some different set point temperatures. So the dark blue buildings have a different set point temperature from the light buildings. And we are simulating different scenarios, and so you can see them blinking. It's because we have night and day set point, and so each time they blink, they go from one set point to the other. Et peut-être que tu peux mettre une température plus basse. Tu peux... So I'm just asking Philippe to put temperature maybe to 93.15 Kelvin, which correspond to 10 degrees Celsius. 93. 83. Allez, vas-y, relance. And so we should see them, blink, and we can see that even for, so during nighttime, we have the same temperature for everyone, so everyone has the same color, but as soon as the day starts, we don't hit them at the same temperature. So maybe we can move on to a next indicator, which is the energy consumption, so Q-flow heating. So as we can see, the color scale here is not very useful because we've got this cathedral who is using a lot of power to heat up. Utilise rainbow. So displaying the different set of color, we can see the heating power necessary to heat each of those buildings to the temperature set point. And we can see the major difference between buildings are the zone volume. And so the building that will need the most heat in the city and the most heating power will be the bigger one for now. And as we will progress with refining our simulation, so we produce all of our model correctly, and then we just need to refine the parameter for the different type of building and the different surfaces of buildings. But we can see that the differentiating variables for heating power is the surface and volume of the building, with of course the cathedral that consume the most heating power since we are simulating it. Maybe you can move to Q-flow. So it's quite an interesting question, and it's quite a correct question. So the flat building consume a lot of power. The reason is they have very large surfaces in contact with the exterior. So you've got large surfaces with a small volume, and so you have to heat it a lot to obtain the correct temperature because you have heat flow with the exterior, which is quite high. So as you can see, they are very flat, so they have a large roof, and this roof provides a large surface to exchange with the ambient air temperature. Philippe, c'est les bons modèles, c'est les modèles qui sont à jour, selon vous pas? So I'm just asking Philippe if we use the latest model or not.
No.
So the other thing is, as I said, we benchmarked our models. So currently it's on a branch in GitHub and we haven't merged yet. So these are the old model. But when we benchmark our model, we realized that the buildings didn't receive as much solar radiation as they should. And so you can see that it's another reason why the flat building consumes so much is because the solar radiation on the roof weren't taken into account. No, it's the case in our new branch, but for this simulation, it's not the case. And so it's another factor that can explain why they consume so much. It's because during the day, they don't receive as much free gain as they should. So maybe we can move to Q-flow cooling just to have a look and to see during which part of the year we are simulating. And so if we are simulating during winter and we inputted the correct scenarios, you can see that we don't have any cooling. Oh, and I hope my explanation was clear about the flat building. So please tell me if I was clear or if I need to repeat something. And last but not least, we can run to the exterior temperature. And yeah, we need to rescale. You can put 273, so that's 0 degrees Celsius and 20 degrees Celsius. So let's have a look. And you can see that the surface temperature of the building the surface temperature of the building will vary slightly. So for the moment, as we are using the old models and we don't take much solar shading into account, and we don't take into account solar gains as we should. There is only a slight variation in surface temperature between each building. So this is correlated to the interior temperature. So as we have said, we have different set points for different buildings. So you can see that the buildings that were heated at a different set point have a different surface temperature from the other buildings around it. But you also have a slight difference of temperature for the walls compared to the roof. Since we don't take into account the solar radiation as we should, the roof are not heated as much as the walls, and so it's clearly shown here. And so next time, when we have integrated the correct models, we should be able to see temperature difference for the roof, which should be much higher than the walls around them because they are more directly impacted by the sun. And also, we should be able to see a difference of surface temperature because of the solar mask on the different roof of the building surrounding the cathedral. And so maybe you can show for the last part the solar mask, and we can see how it affects buildings in load zero. So yeah, let's just rescale the color map. So we start during the night as we did. And we can see for each day that is simulated, you can see the sun moving from, so you can see the shadow moving from west to east since the sun is in the opposite direction. So, est-ce que tu peux mettre en pause au début du journée? So I'm asking Philip to pause at the beginning of the day. And so you can see that the cathedral is starting to project a huge shadow on the buildings around it, since it's a very huge building in the city. And you can see that the orientation for the cathedral is correct. So it has its feet to the west where the sun sets and its head to the east where the sun rises with so this model is not very detailed, but you should have the cross in the middle facing the south and the north. And yeah, you can see that some buildings really do affect their environment, and it's important to model the solar shading from those buildings for the buildings around that. So maybe that's it for this first part of the day. and we will take a short break, and then I will present you some aggregated results. So I will go back to Ktirio cases as we have shown you yesterday, and then I will show you a small Python notebook, and I will comment the curves. Unfortunately, we wanted to produce an ensemble runs, but we didn't have enough time, and we had to improve the ensemble run branch. So I will only be presenting the variability of the deterministic simulation, but the variability of buildings regarding the different KPIs that we will show. So we can see how we can aggregate different type of data to provide a more comprehensive look on the city simulation. So thank you for your attention, and maybe we can take a short break, and we'll be back by 11. So during the break, I also had an idea to better explain why the buildings that are very flat have high energy consumption. So another metric that you can use in building design is the capacity of the building. So it's a ratio of surface to volume. So if this ratio surface to volume is big, that means that you have a surface that is very high compared to the volume, and thus you have some more heat losses for this type of building. You can have an analogy regarding this kind of behavior, and you can see it in nature. So if you take small animals, they have a higher heart rate than bigger animals. And that is because they have a capacity that is much higher than bigger animals. So they have a higher heart rate because they need to produce a power to heat them up that is much higher than the bigger ones. And it's the same for buildings. So if you have high volume, high surface to volume ratio, you need also to have greater power output. So that's a bit of trivia that is interesting to keep in mind when you to remember why some buildings that have a higher surface to volume ratio needs more heat to heat up. So coming back to our main presentation, so we have seen that we can display some different metrics and represent the data on a geographical display using ParaView. So when developing our software, in the end, we want to display those metrics directly inside the software. But to better understand the city, we also need to have some metrics that are not geographical, but aggregated data. So we introduce a little bit our website where we display some cases, where we run some simulation. So just as you did, we have cases, and that's why we use this case. We have Strasbourg. We also have a page for this case. And you can see that we display a number of metrics. So I won't go over the metrics for the weather since we talked a lot about it yesterday, but we can have a quick look at some of the metrics regarding the ambient, the interior air temperature. So in ParaView, it's not very easy to visualize correctly the temperature inside the buildings since they are changing over time. But displaying it as aggregated data over the years for the entire city, we can check if we model correctly the different scenarios for heating and for cooling. So as we have seen previously, so this is weather data file that is correct for the northern hemisphere. Actually, it's a weather data file that was extracted from meteorological data that were collected by a weather station near Strasbourg. The three temperature curves that you can see displayed here are so the exterior temperature in red. Ambient temperature is actually the temperature, the surface temperature of the building's wall that are aggregated. And finally, we have in green the interior temperature. So first, we can quickly check if we model the scenario correctly. So let me zoom during a week in the winter time. And we can see that we have a scenario that is applied for the entire duration of the winter months, where we have a set point temperature of 90 degrees and a drop in temperature during the night of a few degrees. So we go to 18. That's because we modeled the buildings with high thermal inertia, so the drop in temperature is not very drastic. We can see for Friday, so you've got the week with Monday, Tuesday, Wednesday, and Saturday and Sunday. We have different set points, and we can see that we only hit the buildings differentiating the different day of the week, and we don't hit the building during the Sunday. So that's one way to use this graph. The other way is we can see that we correctly reduce the heating power during the summer months because we don't need to heat as much the buildings. And if I zoom a little bit, we can see that we maintain, when the temperature is quite low, we maintain the temperature in the buildings at correct set point. You can see also in blue that the temperature of the wall are a little bit higher than the exterior temperature. And that's because if I zoom on a day, they receive some solar radiation. So the difference in temperature during the day is greater between the surface of the wall and the exterior temperature. And at night, the delta T is reduced. So we can see we still take into account the solar radiation. And as I said, the only error that we had in our model that we have changed now is we don't take into account the solar radiation of the roof. So when we will update the model, we should see a thermal peak that is much higher. So this graph was, we tried to represent the occlusion factor. And so what you see actually is the different courses of the sun. So this is, so we go from 1 to 0. So 1, we block solar radiation, and 0, we let all the solar radiation pass. As we are aggregating data for all the surfaces, so we've got the, as I said, the roof where we made a mistake and they don't receive any solar radiation. And you've got the northern wall, so we can't go to 0 because we aggregate the data of all the walls. And when we are calculating the shading factor, the northern wall doesn't receive much solar radiation, so its value is closer to 1. And we can see that we've got a mean and a max aggregation, and it's a daily aggregation, so that we aggregate for the whole building, and we display the mean and the max. And what the mean shading coefficient factor shows us is that during the winter time, the sun rises quite late and it's set up quite early. So we've got a day that lasts from 9 hours to 6 p.m. But for summertime, the sun rises quite early and sets quite late. And that's why it's interesting not only to have the mean, but to display some mean and max value. And finally, you can see that we display the heat flow for the buildings, and we've got power output for the ideal heating that is much higher during the winter time. But you can see around December that it has a drastic drop. That's because we set up some scenarios where most of the people will go on vacation at the same time, and they won't heat their house as at a very high set point. So we set a very low set point for this vacation period, and so you can see a clear drop inside on the infograph. So that was just a test to see if we model correctly. A scenario where we change the value during the different day of the week, and also where we change the value over the whole duration of the year, and we set some different values for some vacation time. And the last bit of the graph that we display are some comfort indicators. And so you can see it's PMV and PPD, so predicted mean value. And it should be around 0 or close to 0. So that's when thermal comfort is achieved. And you can see that when the temperature drops, people are dissatisfied. But we need to work on that so we don't calculate this kind of value when we consider that there aren't many people in the building. So that's one way of representing the aggregated data, and that was our first pass on producing this type of data. And now we are working on a second pass, and I will be presenting a Python notebook we did earlier this week. And the idea of this notebook is this notebook, the idea was we wanted to show you some ensemble runs, but as I said, we weren't quick enough to produce the results in time because we had to work on this branch. But we want to show you how we can aggregate data, and as we are simulating a city, we still can have some, what do we say? Some statistical data because we are simulating an ensemble of buildings, and so we can see the variation into of this sample of building. So it's still a deterministic simulation, but we can see the variability inside this simulation. So we did quite a big notebook, so I will only be presenting some of the curves because we are trying to find some interesting graph to show. But the first graph I wanted to show is actually, so it's called final energy, but it should be a final power output, final power time series. So I'm changing energy to power because we are displaying watts, and it's not a cumulative graph. So what we are actually displaying is not an energy, but a power. So we can see the mean calculation of the power consumption for the buildings for a few hours. And what you can see, so it's during the winter time. And when you can see in light blue is the standard deviation for the buildings. So we can see that given certain meteorological data, we've got a standard deviation that get quite close, but on other type of condition, we get a standard deviation that is greater. So that's why it will be interesting to run some sensibility analysis to determine which kind of parameters are influencing the standard deviation and what can explain the differences that we are seeing here. Another thing that we can say about this graph is that you can see a clear symmetry between the low standard deviation and the high standard deviation. This symmetry is mainly explained because we set the parameter of all the building to the same parameter, and so we have differentiating parameter for power outputs will be the volume of the building. And since we have only one differentiating parameter and it's linear, we can see that we have symmetry in standard deviation. But when we start to enrich our simulation and we start input different type of data, so we simulate different type of building construction throughout the city, we should have standard deviation but won't have this kind of symmetry and will be also quite interesting to manipulate and uh, to to how do you say, to exploit. So moving forward, the other type of graph that we produce are graphs. So as you can see, this time is energy. So it's cumulative data. So we don't need to display a graph that we will see will be cumulative. We just need to fetch the last value. And so the total energy that was produced to heat the buildings during a certain period of time. And we've got a difference between final energy and useful energy. And here you have the system losses. So the difference between final energy and useful energy is the efficiency of the heating system that is used. So when you manipulate the data and you simulated the city of Strasbourg, what you use were ideal heating system. But for this simulation, we went a little bit further and we used some model for boilers. And so the difference between final energy and useful energy is the efficiency of the boiler. But as you remember, I presented some use cases. And so if we produce this kind of graph, they are kind of useful for the district heating network since depending on where the building are situating around the heating loop, they will receive useful energy that will be different because you will have heat loss along the pipes connecting all the buildings to the power plant. And so having data that can estimate the efficiency will be much more interesting because for each building you will have different final and useful energy. Because the final energy will be the energy produced at the heat plant, and the useful energy will be the actual energy that arrives inside a specific home. So it's interesting to aggregate them, but it will be also interesting to see the standard deviation for this kind of calculation. You can also see on this graph the distribution across building of the final energy, and so of the final energy. And so you can see that we are using log scale. That is because most of the buildings are using an energy, so have the same volume or a volume that is very similar. So most of the buildings are situated on the left part of the graph because they have volumes that are quite identical. But you can see that there is an outlier just right here. And if you remember, I said that for the simulation that we are running, we are currently simulating the cathedral, and we shouldn't. So we should put a filter for this. But you can see this outlier is the cathedral. Because this volume is so big, it needs a lot of energy to produce heat. And so you've got a difference between final energy and useful energy. And once again, if we are simulating for a district network, it won't be as evident, it won't be as correlated the final energy and the useful energy use. And so, as I said, we can see the average profile for the final energy use. So this time it shouldn't be power, and the standard deviation. And you can see right here, it's power output. And so you can see the power output necessary for the final energy and the power output produced by the useful energy. So you've got a slight difference between the final energy and the useful energy that can be explained by the efficiency of the boiler. And I think, here we are. So I was looking for this graph, and so as I said, it will be quite interesting once we will be simulating for district network to have a look at this kind of graph, because the standard deviation for the useful energy and the final energy should be different. So right now you can see that it's quite similar because we are simulating all the buildings with the same system, but as soon as we will have a connected network, the different usage of energy will provide some different shape of curve between the useful and the final energy. And you can see that we are calculating the mean efficiency, and obviously we can see that the boiler, as this is the same for everyone, we can see the efficiency that we gave for the boiler. So for every watt of energy consumed by the boiler, we arrive to produce, we can produce 0.9 watts of heat. And yeah, that will be it for my part. I wanted to finish this presentation by a discussion with everyone, because I'm quite interested in knowing the type of project that you are working on and the reason why you joined this course. I will be also finishing by saying that we will be doing another course. This time it will be more advanced and it will be specific for city simulation. And we will have time to develop and integrate the different branches that I mentioned during the course for Ktirio. And so you will be able to use Ktirio and you will be able to launch some ensemble runs for city simulation. And we probably will be using HPC simulation for this. And we will be doing this at around the same times next year. So I want to thank you for your attention. I want also to give a warm thanks to NCC Czechia for organizing the course and hosting the simulation on the HPC machine. So thank you, Lucy, and thank you, Wojtek, for your work. I want also to thank Maxime, who helped us on our part to organize this course. And finally, I also want to thank my colleague, Philippe, who helped me to produce the notebooks.
So, thank you, Philip and Gwenola, for your great lectures, great prepared exercises, and the whole course. Also, thank to all HiDALGO team for great work, and also thank to our participants for attendance. I just would like to ask you if you could fill in the satisfaction survey. I put the link to the chat. And if you should receive a certificate of attendance, it is possible. So with that, thank you again, and hopefully see you soon on our future events and courses. And yeah, have a nice day. Thank you. Goodbye.